Okay, so yeah, welcome back, everybody. Happy Wednesday. Um, let's let's figure out what we're doing today. So, as I said in my previous, I guess, class, we are now done with new content for this class. So we discussed for a lot of the last part of the semester, we've been discussing sequences, series, sort of big advanced concepts in series like power series, Taylor series convergence. And then we ended with a couple sort of one-off topics, so sort of parametric equations and polar coordinates. On Friday, we'll have our third test, and maybe I should speak very briefly about how, like what the structure of the test will be. So I'm going to treat this test similar to how I have treated uh, the quizzes so far, in the sense that I'm going to post it to Moodle. You'll have the full 24 hours on Friday to complete it. I'm going to ask you when you open it or when you download the PDF to please take it all in one sitting and to sort of hand it in through Moodle when you are done. Yeah, take it all in one sitting. If you aren't able to print out the quiz, that's okay. Just take it on other paper. Just please do me a favor and label each question clearly, right? Like sort of if you're taking it on extra sheet of paper, label question 1 as question 1, label question 2 as question 2, and so on. And then, for those of you who have been using, say, the Cam Scanner app to take pictures and turn in your work, you can go ahead and do that. I believe there's a way to build a document, right? So you can turn in several pages on a single PDF, and I would ask you to do that. If you're having trouble with that, right? So if you are taking the test tomorrow and you're having trouble sort of like taking these pictures and turning it in, send me an email, let me know. I'll be monitoring my email all day tomorrow until a reasonable time in the evening. So just send me that email. We can troubleshoot over email and figure that out. I'm not going to make this a timed exam. So that was one of the questions I had was, should I give you sort of like the 75 minutes, the way we've been doing in class? And to be honest, I'm happy to give you more time or for you to take as much time as you need to complete the test to a degree that you're happy with. I don't want you to feel that time crunch. I'll make it about the same length as the other tests have been. So I think you could take it or you could complete it in 75 minutes if you were moving quickly. But if you're like me, I personally am a very slow test taker. I personally feel a big time crunch, and that negatively affects my test taking performance. At least it did when I was a student and when I took a lot of tests. And I want you to feel relief from that. So I don't want you to feel that time crunch. So I think it could be something that you could take in 75 minutes. I'm not going to make the test balloon up to be much longer than the others, but feel free to take your time on it. Yeah, I guess as always, please hand in any and all work that you want graded. So that means if you do have scratch paper, that's fine. You don't have to turn in the scratch paper, but if you have graded work on that scratch paper, please either copy it over to the thing that you're handing in or hand in the scratch paper and just make it clear like what the problem is in reference to. In short, if you keep everything reasonably organized, keep the problems more or less in order. If you make it easy for me to follow along in your PDF, make it easier for me to grade, I would appreciate that. Any questions about the test sort of structure or what's expected of you on Friday? Let me know. Yeah, any questions at this moment? Okay, cool. Well, if any questions come up, please let me know. Again, I'll be keeping an eye on my email going forward. So what else? So I guess turning to today's class, yeah, I really don't have an agenda for today. I wanted to begin just by opening it up to see if there are any questions or topics that you want me to cover. I sent out this practice exam. Hopefully you've had a chance to take a look at that. I will send out solutions to the practice exam immediately after this class. So I'll send out solutions to all of you. But I wanted to give you a chance at first to look over it and to give it an honest effort on your own. And so if there are any questions from the practice exam, if you've had a chance to look at it, and if you found certain problems to be really challenging, let me know, and I would be very, very happy to discuss those. Just enter it in the chat over here. So I'm happy to talk about any or all of those problems. I am also happy to just make up my own problems. But yeah, if there are different topics that you are interested in seeing, please, please, please let me know. I'm going to go ahead and just pull up a whiteboard here so we can record any information that you all want to see. Okay, so sort of feel like I'm shouting into the void here. Hopefully you can still see the whiteboard screen. Oh, perfect. Hey. I've got some questions here. I love it. Okay, so some problems directly from the quiz. I'm sorry, directly from the practice exam, number 6, number 7, as well as some information on sequences and some parametric curve stuff. Okay, I love it. I love it. Let me go ahead and clear the whiteboard, or let me stop sharing that. And number 5. Okay, this is great. Thank you all so much. I love your questions. Let me go ahead and share. Oh my goodness. Where is the share button? For those of you who snuck in a moment late, my cat is sitting at the base of my screen, and so I can't actually see the buttons that I'm clicking on. There we go. Okay, this is what I want. Okay, hopefully you can see this practice test. Again, I will send out solutions to everything down the road, but in the short term, let's go ahead and talk through some of these. And maybe I'm just going to go in order of the test for the moment. So we'll be able to hit, we've had questions on sequences, on problems 5, 6, 7, and parametric curves, which are later on this. We should be able to talk about all of these. And I'll give you some nudges, at least, for each of those questions. Okay, so first of all, sequences. Sequences were the very first thing that we talked about in this new setting. This was the week before spring break, so of course everything was a little weird. We were sort of, I think over the course of that week, we took the test on Monday, we had a sequence day on Wednesday, and then a sequence day on Friday. And we went from really not knowing what was going on as far as SU being open or closed on Monday to thinking that there was a couple week delay starting on Wednesday to possibly by Friday, we knew that it would be remote teaching for the rest of the semester. So that was a week in which a lot of stuff happened. And I know a lot of you were in different stages of packing up your dorms or trying to figure out your next move. In general, I know that sequences were not top of your list for priorities at the moment. So let's remember a few basic facts about sequences. First of all, a sequence, and hopefully you all can see this. Please let me know if you can't. But sequences were expressions of the form, they were just infinite lists of numbers, right? In which we had a starting point, that could be the number a sub 1, and then we had a sub 2, a sub 3, and so on, and that would go on forever, right? And sometimes we would call this sequence a sub n, with little parentheses around it. and that would represent this infinite list of numbers. When we get to series down the road, right, series, which we're now much more comfortable with, but series are actually the more complicated objects. Those are infinite sums of numbers. So a series of a sub n's, that's like something a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus dot, dot, dot. So we can see that this, the series object in which we add up infinitely many elements is actually more complicated than the sequence object in which we just list them all. And when it comes to a sequence, the sort of key things that we're interested in are, first, determining what a sub n is based on the formula. And we're actually really good at this now. We've done the same thing for series, right? So looking at a formula, like if we had a sub n equals -1 to the n plus 1 divided by n minus 1 factorial, I'm just making something up here, we would know how to calculate a sub 4, right? A sub 4 would be -1 to the 5th, so that's just a -1, divided by 4 minus 1 is 3 factorial, so that's 6. So we know how to look at a formula for these a sub n's and calculate what a given a sub n is. We do that in series all the time. The other big things that we cared about in terms of sequences were we cared about sequence convergence. And sequence convergence looked very, very similar to function convergence or function limits at infinity, right? So we were interested in knowing as our n values got bigger and bigger and bigger, what would a sub n converge to, if anything, right? And so let's look at an explicit example here. I'm just going to make it sort of nice and easy. Let's say a sub n equals 1 over n, right? And we're interested in knowing whether or not the limit as n goes to infinity of 1 over n converges. We're interested in knowing what that expression might be. Well, it turns out that this is basically identical to the question, what is the limit as n goes to infinity? I'm sorry, this is basically identical as the expression, what is the limit as x goes to infinity of the function f of x equals 1 over x. This expression over here that I've written in purple, this is about looking, or this is a problem that involves looking at functions and looking at a limit at infinity for the function f of x equals 1 over x. And so our go-to strategy here is really just to sort of think through, as my x values get bigger and bigger and bigger, what happens to the given function? Well, as my x values get bigger, my f of x values, right, they actually get smaller. My denominator is getting bigger, my numerator is staying the same. And so overall then, this entire expression should end up going towards 0. And so we would get, just through thinking through this calculus 1 style, that the limit as x goes to infinity of 1 over x equals 0. We do the same thing with our sequences. And so our sequence problem over here, we get the exact same answer. The limit as n goes to infinity of 1 over n is just going to equal 0, because as n gets bigger and bigger and bigger, the denominator gets bigger and bigger, and so the overall fraction goes to 0. Now, we did have one extra trick when it came to sequences, and that was the monotone convergence theorem. This is something that I believe we talked about that Friday before spring break, so it's possible not everybody saw this to the extent that maybe we might have wanted. And so that's actually the reason why I put this on the practice test, as opposed to just sort of springing it on you for the test, is I wanted an opportunity in this Wednesday class to talk about the monotone convergence theorem. So the monotone convergence theorem basically said that if a sequence is monotone, right, so if you have a sequence a sub n, and if a sub n is monotone, and monotone means it goes in only one direction, so it's only increasing or it's only decreasing. And I'm actually going to be slightly more specific there. If a sub n is monotone, meaning it is either non-decreasing or non-increasing. And a slick way to say that is that a sub n plus 1 is always greater than or equal to a sub n, meaning that our sequence, as I go from one term to the next, is either staying the same or increasing or inching up. Right? So if a sub n is monotone, which means either this is true for every term, or the opposite is true. A sub n plus 1 is less than or equal to a sub n for every term. Right? So if either of those is true, okay, that was the monotone part. So if our sequence is monotone and our sequence is bounded, and a sub n is bounded, which just means that it does not march off towards plus infinity or minus infinity, right? It stays within some boundary or within some bounded region on the real number line, right? So I'm plugging in real numbers that are, let's say, always less than 10. Then a sub n converges. Right, so that's just an extra trick when it comes to sequences to determine whether or not a sequence converges. The example that we gave in class was sort of a fun but silly one. If we take a sequence that looks like this, right? So the sequence was let's say, so the sequence a sub n was, let's say, 0.1, 0.12, 0.123, ... right? So I'm just adding on to this decimal. Eventually I could get 0.1, 2, 3, 4, 5, 6, 7, 8, 9. And then if I'm going to go to 10, I'll just add on another 10. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and etc. Right? If I'm just adding on to this decimal, my sequence is always increasing, right? Every term, as I go from one term to the next, is just getting slightly bigger, ever so slightly bigger. So my sequence here is increasing, and it's monotone, but it's also bounded, right? Because no matter how many terms I add on, this is never going to get above the point 0.2. It'll stay bounded below the point 0.2. So even though this sequence, you know, I don't have a nice way to write what it converges to, because it's always increasing and it's bounded, it never gets above 0.2, it is definitely going to converge. So this converges to some irrational number. Okay, and that's the monotone convergence theorem. This one sort of extra element when we talk about sequences and sequence convergence. We actually secretly use sequence convergence a lot when looking at series, right? So worth saying out loud, remember that in order to tell whether or not a series converges, what we did was we looked at the sequence of partial sums, right? So we looked at the S sub n's, where S sub 1 was just equal to A1, S2 was A1 plus A2, S3 was A1 plus A2 plus A3, and so on, right? So S sub n would be the first n terms of the sequence added up. So these are all the partial sums, and then we looked at the sequence of partial sums. So we looked at the sequence S sub n, which is S1, S2, S3, S4, ... and we saw whether or not that sequence converged. So we have this sort of theory that says the series converges if and only if this sequence of partial sums converges. And that's how we can think about series convergence. And that's why we can say, for example, that the series that looks like plus 1, minus 1, plus 1, minus 1, plus 1, minus 1, etc. All of those end up, or that series ends up diverging, right? Because its sequence of partial sums was First it was the number 1, then it was 1 minus 1, then it was 1 minus 1 plus 1, etc., right? And this sequence just bounces back and forth between 1 and 0, never converging to any specific number. So that, in a nutshell, was sort of our conversation on sequences. The big ideas being this sequence converging if and only if sort of the corresponding function converges. The monotone convergence theorem, the sort of extra argument that we have, and the idea of a series converging being related to its sequence of partial sums converging. That was sort of our main thrust from those days on series. I'm sorry, those days on sequences. Okay. Any quick follow-up questions? I wanna move along, make sure I can answer all of the questions that you all asked, but I also don't want to leave anything hanging. So any questions about what we just shared? Okay. Okay, I'm going to go ahead and clear this this stuff. Let's scroll down to, I think problem 5 was the next one.
Can I kind of clarify what I had issues with?
Yeah, definitely.
Last class you said something about just kind of, okay, well, I found using the alternating series test, I had that, but then when I had to do the absolute value one, I just kind of didn't know. That's the one where you have to, like, you can apply any test. So just kind of like how you know what test to apply out of all the tests.
Yeah, that's a great question. Ooh, and that's a much broader question than just specifically number 5. So yeah, thank you for clarifying. So the question, well, question 5 asks about whether or not this series converges absolutely, conditionally, or whether or not it fails to converge. More broadly, there's this question of how do we know which series test to use if we're just given an arbitrary series? Okay, that's a great question. I'm not going to directly answer problem 5 immediately. Instead, let me sort of describe my thought process for looking at a series question, right? And if I'm given an arbitrary series, what do I do? So the very first thing I do is I check to make sure, so maybe I could call this like a series flowchart. I don't think flowchart is the right word, but sort of a thought process flowchart. I'm just going to say series thoughts, right? And this is sort of the order in which I do these thoughts. I'm not going to fill in a full flowchart. I think that would take too long. But thoughts on how to approach a series. First of all, I just want to make sure, do the individual terms, the a sub n's, converge to 0? Right? Because if I did something kind of silly, like 1 plus 2 plus 3 plus 4 plus ... like the sum of n, that's clearly going to diverge, right? Anything that does not converge to 0, if the individual terms do not converge to 0, then the overall series will absolutely diverge. You'll end up adding up, like, you know, the same thing over and over and over again. Or you'll be adding up something big over and over and over again. So do the a sub n's converge to 0? If they don't, then the series diverges. And we called this the test for divergence. So maybe this is a slight flowchart. If they don't, it definitely diverges. And that was the test for divergence. If they do, then my first big question is it a geometric series or a p-series? Because those are the two where I immediately, I mean, we have to remember the rules, but if I recognize it as a geometric series or a p-series, then I immediately know my answer, yes or no. It definitely converges or definitely diverges based on the specific requirements of a p-series or a geometric series. So if the answer here is yes, then we solve using the appropriate geometric series or p-series strategy. If the answer is no, I might, and let's think through this. If the answer is no, then I might see whether or not it's an alternating series. Right? And if it's an alternating series, and the answer is yes, I will try to use the alternating series test. I'll try to use the alternating series test, which, Gabrielle, it sounds like you did here. So this is an alternating series. You can use the alternating series test to show that this does converge, right? So the original series converges. Jumping back to problem 5 for a second, this converges by the alternating series test. And so as a result, what was I just going to say? Yeah, as a result, our original series either converges absolutely or converges conditionally, but it definitely doesn't fail to converge. All right, so if we do not have an alternating series, right? Or maybe I should say if all terms are positive, right? Or at least non-negative, if all terms are positive or at least non-negative, then there are a few other series tests that we have to think about. Those include the integral test, the ratio and root test, I guess the ratio and root test, and the comparison or limit comparison test. So those are other tests that we can think about. And that's why this is sort of at the very end of this flow chart, because there's a lot of additional tests that we have to think through. So at this point, it becomes a little bit more challenging to figure out which test to use, but bullet points that we can think about to determine are, could we integrate a sub n, right, treating it as a function of x, right? And in that case, right, I'm thinking about finding an antiderivative and evaluating the integral from 1 to infinity. That was our integral test. So we could use the integral test there. I could think to myself, does it look like, or does it have a lot of exponential expressions, factorial expressions, or polynomial expressions that are already in a fraction form? So is it a fraction with, expressions raised to the n, factorials? Man, I hope this is legible and makes sense. Let me know if it doesn't. But is it a fraction with things raised to the n, factorials, or like polynomials involving n? If so, we could consider using the ratio test. Because oftentimes when we have these fractions and we use the ratio test, we get like a fraction divided by a fraction, and a lot of great cancellation occurs. And we've seen that happen a number of times. If it just has an expression raised to the n, so if the entire thing is raised to the n, try to use the root test, right? The nth root test. Because then when you take the nth root, you'll cancel out that n in the exponent, and that will make it a lot easier to deal with. And finally, if it doesn't fit nicely into any of these boxes, but it looks similar to something that does, use one of the comparison tests. So if it's messy, but looks kind of like, and I'll try to clarify that in a second, but looks kind of like a nice series. I guess messy and nice should probably be in quotation marks. If it's messy, but looks kind of like a nice series, use a comparison test. Okay, look at that. So we did end up getting more or less a full flow chart here. In short, right, I'm going to sort of start with the easiest tests to use, sort of the ones that I can quickly verify and for which I'm most confident in. And I'm going to sort of go down the flow chart until I get to some of the more challenging ones, like the comparison test. And it turns out in this problem, to figure out whether it converges absolutely, we will probably want to use the comparison test. So let's turn back up to the problem here. And let's think about whether or not this converges absolutely. Well, if it converges absolutely, then I'm interested in examining the absolute value of -1 to the n over the square root of n plus 1. Right? And that's just going to be the sum of 1 over the square root of n plus 1. Okay, so it sounded like in the question that this is probably where the challenge came in, is looking at this expression and trying to figure out how can we deal with this. Well, let's go down the flow chart, right? So the flow chart, do the individual terms converge to 0? Yes. Is this a geometric or a p-series? No, right? A p-series is of the form 1 over n to the p, while a geometric series has this common ratio, like an r to the n. This has neither of those. So unfortunately, it's not geometric, nor is it p-series. Is it an alternating series? No, we threw in the absolute values, so all of the terms are positive now. So we're in this final set of bullet points. Okay. Actually, there's a few different things we could do at this point. Can we integrate this? Yes, we technically can. So when I talk about integrating this, I'll do this in pink. When I talk about integrating this, I mean taking the integral from 1 to infinity of the expression 1 over the square root of x plus 1. Right, so converting that series into a function and converting, well, I should say converting the terms into terms of involving x, and converting this infinite addition, this infinite series, into an integral. And the idea was that one of these would converge if and only if the other converged. So we can check this, and we can see, in fact, that this integral diverges. But that's actually itself not completely straightforward. We would have to do a u substitution with u equal x plus 1. And we would have to use improper integrals, right? Since it's an integral as we go to infinity, we'd have to take the limit as b goes to infinity of the integral from 1 to b, and we'd end up getting something like 1 over the square root of u du. So we can go through those details. We'll end up seeing that this diverges, the integral diverges, and therefore the resulting series, or the original series, diverges. So we can use the integral test here. We end up having to put in a little bit of work, but we see that this series diverges. And therefore, the answer to question 5 is going to be that it converges conditionally. Boop. Cool. Okay, if we didn't want to go through all of that, or if we got to this point, right, the integral point, and we saw that we forgot how we could integrate that, there are other strategies that we could use. So let's talk through one more of those strategies. Is it a fraction raised to the nth involving factorials, involving polynomials? Not really. Yeah, it doesn't have any, yeah, just no. It's a fraction, but it's not a great fraction for the ratio test. Similarly, it's not great for the root test because it's not raised to the power n. But I think this final bullet point could work. This is an expression that is messy, right? The 1 over square root of n plus 1 is messy, but it looks like a nice series that we know. So it looks like, right? It looks like the series 1 over square root of n. Right, so this is what I mean when I say something's messy, but it looks similar to a nice series. That plus 1 is kind of complicating the series expression. But if I got rid of the plus 1, it looks like a nice series that I already know a fair bit about. And so the question is, can we use the comparison test here? And it turns out the answer is yes. The explicit details will be on the answer key that I'll hand out after this class. But in short, this looks like 1 over the square root of n. It looks like it in the correct direction. So we see that 1 over the square root of n plus 1. Oh, no, it's actually in the wrong direction. It's actually in the wrong direction. So 1 over the square root of n plus 1 is less than 1 over the square root of n. But 1 over the square root of n diverges. So let me actually start there. Let me back up. The 1 over the square root of n, this diverges. And how do we know that that diverges, right? This is a nicer function than the one we were originally looking at. How do we know that that diverges? Well, again, if we go back to our flowchart, this was nothing more than a p-series. This was a p-series because we could think of it as 1 over n to the 1/2. So it was a p-series with p equals 1/2. And our p-series test says that that diverges. It's less than p equals 1. So this diverges. And so I could try to compare these two series. And I can do that not with the comparison test, but with the limit comparison test. So I can take the ratio of the one series divided by the other. I can take the limit of that as n goes to infinity. And because it's a finite number that I get as a result, it turns out to be, I just get 1 as my number, but because it's a finite number that's not 0, these two series either both converge or both diverge. And since this blue one diverged, so would the darker blue one, right? Because this lower one diverged, so would the one up here. So either way, we will get, so both of those I think are sort of challenging to go through, either the integral test or the limit comparison test. But either way, we'll get that this series diverges when we throw on the absolute value signs. And so the original series converges conditionally. Any questions about that?
Wait, so you would use the limit comparison test when Bn diverges?
So that's a good question. I guess I sort of glossed over the comparison test versus the limit comparison test. They are both tests that let us compare one series to another. Yeah, they both let us compare one series to another. I think the regular comparison test is often easier to implement, but the limit comparison test is more powerful. It works in circumstances when the comparison test does not. So the limit comparison test is a little bit harder to use, but it's more powerful. So in this case, I would say it's not the fact that it diverged, but it's the fact that it was the wrong inequality for divergence. What I would have liked to do, right? Maybe I'll put this as an aside over here. What I would have liked to do is I would have liked to compare a series a sub n to b sub n. I would have liked to be able to say that a sub n was always less than or equal to b sub n. And I would have liked to say that b sub n converged. Right? So if b sub n converges and a sub n is always less than b sub n, then a sub n will also converge. Alternatively, I could have done it like this. So I could have said, if b sub n is always less than or equal to a sub n, so a sub n is the bigger sequence, or the bigger series, and if b sub n diverges, then a sub n will also have to diverge, right? Because it's larger than something that's going off to infinity. the trouble here was that I got the incorrect inequality to be able to say something meaningful. In the example at hand, let me throw up the right colors. At the example in hand, I had my sum of a sub n, because that was actually bigger than, or I'm sorry, that was actually smaller than the sum of b sub n, right? Because the n plus 1 in the denominator here made it smaller than if I just had n in the denominator. So I had that inequality, but I had that this expression diverged. And that's not the correct sort of direction that we would want to go. So then I'm trying to make a conclusion about a series that is smaller than something that's infinite. So this could be infinity, or it could be something finite. The way that this is set up doesn't allow me to draw a meaningful conclusion about that a sub n, right? To say that it's less than something infinite isn't saying that much at all. Less than or equal to something infinite. So that was the issue there, Jose. So when I tried to quickly do the comparison test, I realized that my inequality was not the direction that I wanted, and so I jumped into the limit comparison test, which actually did let me compare these. Cool. Yeah, any other questions about any of this? Okay, great. I'm gonna, again, I think there are some more details in the solutions. However, one thing that I don't explicitly say in the solutions that we did talk through here, so I just wanna make it explicit, is this sort of flowchart idea. I guess I should have highlighted even more than that. This series thoughts, I think, is a great way to sort of think through these questions where you get a series and you're not quite sure how to proceed. I'm going to clear all of this. Let's keep sliding down. We want to talk about problem 6 and problem 7. I'm going to focus primarily on problem 6b because I do think that is the clunkier example to talk through. When it comes to problem 6a, it really comes down to using this definition specifically at these points here. And I should really have said here, this is like at a equals pi, not specifically x equals pi. So in particular, we would have to calculate the different derivatives of f. So f by itself was cosine, f prime is negative sine, f double prime is negative cosine, f triple prime is negative positive sine. So we'd have to calculate all of those. And then we would have to plug in the point a equals pi. So in order to get, in order to calculate this expression up here, we would need the kth derivative of our function evaluated at the point a, so evaluated at the point pi. So we'd have to calculate all of these things at pi, right? So cosine of pi is -1, sine of pi is 0. This becomes a +1. Let me write that better. That just becomes +1. And then sine of pi is again 0. So we have to know all of those facts. But once we do, this just becomes a matter of plugging in, there we go. This just becomes a matter of plugging into this entire equation up here, right? And so we would get -1, that's our first term, plus 0, that's our second term, plus 1 over 2 factorial, x minus pi squared, plus 0, that's our third term. Oh, and because this is p sub 4, we'll actually need a fourth term. So f to the fourth derivative, right, which we'll often write as f parentheses 4. That's cosine again. I need cosine of pi, so that's going to be -1. So finally, we would end up with a negative 1 over 4 factorial x minus pi to the 4th. Okay, so for this sort of, represent the Taylor polynomial kind of question, it really came down to using the formula and knowing how to use the formula. The second question also involves knowing a formula, knowing how to use a formula, but it's more challenging. It involves this error expression. And so the error expression is always about trying to find a bound on the error at a given x value. So trying to figure out what e of x is less than or equal to. So we need e of x to be less than or equal to, I'm just going to basically rewrite this, some constant m, which we need to figure out, times the x value we're looking at minus the point that our Taylor polynomial is centered around, all raised to the n plus 1, where n was the order of the Taylor polynomial, like so what degree the polynomial was, all divided by n plus 1 factorial. So for 3 of these constants, x, a, and n, it just involves looking back at the equation and trying to identify what's what. So in our problem here, we're told that x is 3 pi. So we got x equals 3 pi, because that's where we're interested in evaluating the error. We centered our polynomial at a equals pi. This is back in part A up top, in the first part up top, so a equals pi. And we looked at a 4th order polynomial, so n equals 4 here. So we've got most of this already. The challenging part always, I mean, it's all kind of challenging, but the most challenging part always is figuring out what m is. So m is chosen to be larger than the n plus 1th derivative in between x and a. So we need to go back to our original function, that was f, right? So f of x was equal to cosine. We need to calculate the n plus 1th derivative, so that's the 5th derivative, which the 4th derivative was cosine, so the 5th derivative will again be negative sine of x. And we need to figure out in between pi and 3 pi, how big does that 5th derivative get? So the 5th derivative, which is negative sine, doesn't get bigger. I should say here, this should be bigger in absolute value, because we also don't want it to get too negative. The sine function actually never gets bigger than 1, right? And that's true because if we examine the sine function between pi and 3 pi, right? Our sine function would start at 0 here. It sort of looks like that. But it never gets bigger in terms of height, right? It never gets bigger than 1, and it never gets less than negative 1. So m is supposed to be a bound on how big that 5th derivative gets. And now we see that that 5th derivative never gets bigger than 1. So we can go back and we can choose m to equal 1. And so when we tie that all together, we're going to end up with the expression e of x is less than or equal to 1 times 3 pi minus pi, so that's 2 pi raised to the 5th divided by 5 factorial, right? AKA the error is less than, what is that? So 2 to the 5th times pi to the 5th, so 32 pi to the 5th divided by 5 factorial, which is 120. So that gives us an explicit bound on how far off our error can be, which is really what we were aiming in this problem, and that would be our explicit answer. So e of x is less than or equal to all of that. So just like in the problem above it, 6a, this really comes down to just sort of knowing what the problem is asking, right? Specifically, its answer should be of the form like e of x is less than or equal to something, and then sort of going through and figuring out what we're plugging in for x, a, n, and m, with m being the especially tricky one to figure out. All right, cool. Let's talk about problem 7, and then we'll close by talking about some parametric equations. I also want to say, like immediately after this class, I have office hours, and I don't anticipate that many people from outside of this class coming to office hours. So in the other class that I teach, I don't anticipate that many people coming. So if anybody wants to talk about any of these in more detail or talk about any other problems, and you're free, starting at 9:30, just stick around. We can keep talking. But in the time we have sort of officially for this class, let's talk about problem 7 and let's talk about some parametric equations. I love problem 7 because problem 7 is a quintessential kind of series question, or a Maclaurin series / Taylor series question. In the problem above, problem 6, we computed a Taylor polynomial just by sort of basically plug and chug and calculating all of this stuff here, right? Specifically, we had to calculate the f, kth derivative of f at a. So we looked at f, we calculated f prime, f double prime, f triple prime, f fourth of prime, f, quadruple prime, and plugged in a each time. That's great. And that gives us a nice way to calculate a Taylor polynomial or a Taylor series. Problem 7 gives us a different way to calculate a Taylor series, or in this case, it's a Maclaurin series, which is just a Taylor series centered at a equals 0. It gives us a way to calculate that, or I should say, it gives us a prompt to calculate that using a different strategy. And the strategy here is to look at the expression that we're trying to compute and identify a piece inside whose Maclaurin series we already know. And in this case, that's e to the x. So the expression that we have here, sort of the big boxed red expression, is saying take the function e to the x, multiply it by x squared, and then find an antiderivative of it. So what we need to do to find the Maclaurin series for all of this is to do exactly that process, starting with the Maclaurin series for what we already know. So that's the e to the x. So the Maclaurin series for e to the x is, and let's sort of write that out. So e to the x, I could write it in either sort of summation notation, right? So that was n equals 0 to infinity. What was that? That was 1 over n factorial times x to the n. I can either write it in that form, or I can write it as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on and so on. Right? There's secretly here, there's secretly a 1 factorial, but that's just 1. Here there's secretly a 0 factorial, but that's also just 1. So I can write it in either form. And then, right, let's think through what we did up above. We started with e to the x, we multiplied by x squared, and then we integrated. So if I multiply by x squared, right, I'm going to have the same expression from before, but with an x squared multiplied out front. And our rules of series manipulation say that I can do that, or I can accomplish that by multiplying every term by x squared. So I get x squared times all of that, but I can perform this multiplication term by term. So this becomes an x squared. This next term becomes an x times x squared, so that was an x cubed. This goes from being an x squared to an x to the fourth. This becomes an x to the fifth. This becomes an x to the sixth, and so on. And so I can write this expression, right? This was written as sort of my series for e and then multiplied by x squared on the outside, but I could rewrite this as the sum as n goes from 0 to infinity of 1 over n factorial times x to the n plus 2, right? X to the n times x squared, I would get x to the n plus 2. And notice that as I've multiplied by x squared, that is exactly, like what I've written down here, is exactly what I had up here. So we took e to the x, we multiplied by x squared. Now the final thing that we need to do is we need to find an antiderivative of it, right? So let's find an antiderivative of x squared e to the x. And to do that, I can again take this expression, but I can integrate term by term. That's sort of the takeaway message for these kind of manipulations, is what I want to do to the whole function, I can do term by term for the Maclaurin series / power series. So hang on, let me rewrite this. We've got x squared over 0 factorial plus x cubed over 1 factorial plus x to the fourth over 2 factorial plus x to the fifth over 3 factorial. Let's stop there, plus dot, dot, dot. So to integrate, I can integrate this term by term, integrating each of these pieces, and each of those pieces can be integrated nicely in a straightforward manner. The first one becomes an x to the cubed, x to the third, x cubed over 3 times 0 factorial, right? The 0 factorial stayed, but when I integrated x squared, it became x cubed over 3. So that's where the 3 came in. So that's 3 times 0 factorial plus the x cubed became an x to the fourth over 4. There's still a 1 factorial there, plus the x to the fourth became an x to the fifth over 5 times 2 factorial. The x to the fifth became an x to the sixth over 6 times 3 factorial. And we can see the pattern that we've developed here, right? The expression that we had before, and I'll box this off up here, right? But the expression that we had before, that was this integral of this sum of 1 over n factorial times x to the n plus 2. That can be done term by term. So we get a sum of all of these different integrals. That's 1 over n factorial x to the n plus 2. Right? And when I actually compute that integral, I get the sum of, we can keep the 1 over n factorial, and then we get an x to the n plus 3 divided by n plus 3. And so we can rewrite all of this really nicely, and I'll do that now, to sort of align with what we have down in the denominator. This formal answer is the sum, as n goes from 0 to infinity, of x to the n plus 3 divided by n plus 3 times n factorial. And you can see that what I've written here is exactly what we computed down here. So the recent quiz that you all took, right, the Taylor series quiz involving S24 and S25, the second question The second question on that, one of the most missed questions on that quiz, well, the most missed question on that quiz, one of the most missed questions on you know, everything that you owed me last Friday, had a question of the form integral. It was the integral of, I think it was cosine of x minus 1 over x squared. Right? And so we would now, maybe armed with our knowledge here, we would approach this problem exactly the same way that we approached the problem in problem 7. We would start with the cosine expression, and then we would subtract 1. We would divide every term that's left by x squared, and then we would integrate that. So if you struggled with that problem, first of all, you weren't alone. I think a lot of people struggled with that. It's a challenging problem. But secondly, this problem here, problem 7, gives you a little bit of a blueprint for how you could approach the problem from the quiz. Any questions about that?
So I'm a little confused. What exactly is the reason for why you do the Maclaurin series for e to the x, and then you plug in x squared? What exactly is the reason for why you do e to the x and then plug in x squared instead of take the Maclaurin series for the whole thing?
Aha. So I think so that's a great question. So let me think. So I believe we could actually approach this problem in a number of different ways. So maybe, Carson, if this is getting at your question, I could have taken the expression x squared times e to the x, and I could have taken the Maclaurin series for that. So I could have started there. And then I could have taken the antiderivative of that. If I had done that, I would have gotten a correct answer. But in order to get to that point, I would have had to first find a nice way to write the Maclaurin series for x squared times e to the x. And that would mean that I would have had to take, you know, if that was my f, I would have had to take f prime, I would have had to take f double prime, I would have had to take f triple prime. And every time I would take a derivative there, I would need to use the product rule, because x squared times e to the x is a product. And so as a result, what we would end up with is a complicated expression that I'm then plugging in 0 for. So I could have done it, and it wouldn't have really been an issue, but it would have actually taken, I think it would have been more computationally intensive or taken more time than our approach here, which was just to start with our Taylor series, our Maclaurin series that we already knew, and just multiply every term by x squared. So I think it would have just, yeah. I think it would have just been slightly more challenging, slightly more time consuming, would have gotten us the same answer.
Okay. So, all right.
Yeah. I also think this is a great moment just to have a little shout out for how cool Taylor series are. I mean, this whole class has basically been a shout out for how cool they are. This past week has been a shout out for how cool they are. But I want to point out that this expression, I could have asked a similar question earlier in the semester. I could have asked the question back in mid-February. I could have said integrate, or calculate maybe, calculate the integral of x squared times e to the x dx. And you could have done that. That would have been a test 1 style problem, but it would have required integration by parts twice. You would have had to integrate by parts twice, right? And I'm sure, you know, integration by parts is long in our distant memory now, so who remembers exactly how we did that? But we would have integrated by parts, letting this be our u, and letting the e to the x dx represent our dv. And we would have had to do that twice. So kind of cool that we can look at that expression, right? The antiderivative of x squared times e to the x, and approach it in a number of different ways, either integrating by parts twice to get an answer, or creating a Maclaurin series representation of the answer, starting with a Maclaurin series representation of e to the x. So just like, you know, different ways that we can look at this challenging object. Yeah, and I just think that's awesome. So cool, like, sort of tie into our earlier work this semester. We have about 8 minutes left, and I want to turn to parametric equations. It was the last question that was asked, or the last question that somebody asked in the chat box. So I want to make sure that we have a chance to talk about that. And again, if you all still have more questions, want to talk more, are around after this class, stick around in my office hours. I'll probably just, I'll jump on Discord, but I'll also reopen this room and we can just keep chatting about this stuff. Okay, so parametric equations. Parametric equations are governed by, representing a curve in the xy plane, not by writing x as a function of y, but instead by including two functions, one for x and one for y, that are both functions of time, both functions of t. And so the parametric equations, right, they're often given as a pair. Parametric equations here are written as x of t equals square root of t and y of t equals 3t. We're also given in this problem a range of t values that we're allowed to plug in. Sometimes we're given like an explicit range. Sometimes we're just told that t can be anything, right? So t could range from negative infinity to infinity. In this problem, we are given those two equations and we're told that t has to be non-negative, which makes sense because we can't take the square root of a negative number. Typically, parametric equation problems will come in two flavors, at least at this moment in the semester. Number one, I'm interested in you being able to describe the parametric curve. So based on these equations, what does the curve look like that's getting traced out in the plane? And what direction is it getting traced out in, right? So how does that tracing occurring and what is the result? Big question number one. Question number two, which we ask sometimes, is can we express this parametric equation as a good old function like y equals f of x? And in this practice problem, problem 9, we were asked both questions. So to approach the first question, right, how do we sketch this? My recommendation is to begin, especially at this sort of early stage when we're new to parametric equations, start by plotting a number of points. And when I say plot a number of points, I mean identify a number of moments in time and plot those points. So I would sort of write off in the margin at t equals 0, I might say, what is the expression x of t and what is the expression y of t? So at time t equals 0, x equals the square root of 0, which is 0. Y equals 3 times 0, which is just 0. And so at time t equals 0, we are actually at the point x equals 0, y equals 0. So we are at the origin in space. That's where we are at t equals 0. At t equals 1, right? So I'm just plotting a few points. They don't have to be integers. I could plot t equals 1/2. I could plot t equals pi. I like integers because they're nice and easy to plug in. So at t equals 1, we get x equals the square root of 1. We get y equals 3 times 1, so y equals 3. And that means that after one moment in time, let me go ahead and maybe that's 1, 2, 3. 1, 2, 3. Okay, at time 1, we are at the point 1, 3. So we're all the way up here. And I would do this for a few more points just to get a sense of what my curve is looking like. So let me just do one more. At t equals 2, we've got x equals the square root of 2. We've got y equals 3 times 2. The square root of 2 is like 1.4, and so it's actually going to be sort of right about here. That's time t equals 2. This was time t equals 1. So we've plotted a few points in time, but the idea is that our parametric curve is traced out in time, right? So as time flows forward, all of these points are kind of filled in to create a continuous curve. And our continuous curve in this case, or in many of these cases, we can roughly approximate it by plotting a few points and then more or less connecting the dots in a smooth way. That's not super accurate, you know, and I mean in the sense that we're interpolating here. We're sort of filling in some missing details, and we're hoping that we've got them right. But it gives us a general sense of the curve that is reasonably accurate. So I could just draw straight lines, right? So straight line, straight line. But if I want to connect these in more of a smooth manner, I might draw them in sort of a smoothly flowing curve that kind of looks like this, right? And that would give me a sense of what my curve looks like. I'm given a sense of direction both by plotting or like explicitly saying where our point is at several different moments in time. A heuristic that I really love is to include a little arrow indicating the direction that we're flowing as time moves forward. So as our parameter t moves forward, I started at the origin and then I'm sort of flowing up in that direction. Okay, the second question, eliminate the parameter to write this curve as a function. Well, this cannot be done in every parametric curve. There are some parametric curves, especially the ones that sort of double back on themselves, that cannot be written as a function because they would violate the vertical line test that every function must satisfy. This example, it seems like we're okay. It seems like this function satisfies the vertical line test. The vertical lines only intersect the curve once. So we should maybe be able to write this as a function y equals f of x. And to do that, we'll take our original curves, x equals square root of t, y equals 3t. And my suggestion for doing this is to do the following. We start with our x value, right? And we want to rewrite this solving for t. So we want to solve for t. And we can do that in this case. It's nice and straightforward. I can just square both sides. So I get t equals x squared. Right? So I've solved for t. I have t equals an expression involving x. And then for this expression, y equals 3t, right? I can just use my previous result. So if we said that t is equal to x squared, then my y value no longer is 3t. It can be rewritten as y equals 3x squared. And so I've written this now as a function of x. Notice this is a parabola. And in fact, the shape that we got over here does really follow that parabolic shape. So it does sort of make intuitive sense in this case that we would get that as our function, or that we would get sort of a parabola-like curve as our function. It at least align, or it's evidence that we've completed both part A and B correctly. They kind of agree with each other. So those are the kinds of questions that we are likely to see on a test. Those are the kind of things that we've talked about. The one thing that did not appear here on this practice test was a question that involved the slope of the parametric curve, right? And so the slope of the curve, I'm just going to throw up this equation and then we'll end class, but the slope of the curve, right? Normally, we think of this as the derivative of the function y, so like we can represent it as a dy dx, but we can represent that as a dy over dt times dx over dt, which can be represented as y prime over x prime. So this first expression, dy over dx, that would have been like y prime of x if y was a function of x, right? So that's how we would have addressed the slope of a function back in Calculus 1. And in fact, we did that all the time back in Calc 1. So that's like our Calc 1 approach to slope. The parametric equation approach to slope actually comes from finding the ratio of these two derivatives, right? So this is our parametric equation approach. And so if you were asked to say, find points on the curve where the slope of the curve is equal to 8, I would have to calculate y prime, I would have to calculate x prime, and so I would try to find t values for which y prime over x prime was equal to 8. And in this case, y prime is equal to 3, x prime is equal to 1/2 t to the negative 1/2. And so I would be trying to solve the equation 3 over 1/2 t to the negative 1/2 equals 8. And then we would just solve for t. So that is the final kind of question, like this sort of slope-based question that we did not see on the practice quiz, but that we did talk about in class. Okay, and we're totally out of time there, so I want to stop there. Again, I'm around in office hours, and I'm super happy to answer other questions. Jose, it looks like you might have a question before we part ways, so I'll take that question, and then I will either see you all in office hours over the next few days, or you know, see you in class next week. So if I don't see you, good luck on everything. Good luck on the test on Friday. I'll be checking my email, so let me know if any issues arise, and have a lovely, lovely rest of your week and weekend. So yeah, I'm gonna stop the recording. And actually, oh wait, Jose, you had a question.
I just had a question on the error bound on 6B.
Oh, okay. Let's pause on that for a second. I'm going to stop the recording. I'm going to officially end class, but then I'll stick around and answer any questions that you have or that anybody else has. And this can sort of bleed into office hours. So the recording is stopping. If you're watching the recording, take care. Have a lovely rest of your day.